Well, in the last video, I had said that when you have this the covariance structure, capital sigma theta, then all you have to care about when you are using it is how to specify that capital sigma of theta and leave to the computer the job of estimating the theta parameter by using maximum likelihood. Now, while that is in general true, there are two situations where you can use something simpler than just using the brute force MLE technique, and we are going to discuss them now. The first one is called generalized least squares or GLS. GLS, generalized least squares. This is not to be confused with something else which is called GLM, generalized linear model, that we will discuss later. So in this case, we have this setup. Capital sigma theta is of the form sigma square times some p. So sigma square is your unknown thing and p is a known thing. So unknown, and this is known and pt. So if your capital sigma theta is of this form, which means theta is just a single number, that is sigma square, then you can fit the model much more easily in the following one. So your model is y equals x beta plus epsilon, where epsilon has mean 0 and covariance matrix is. So what we will do is, we will take a square root of p. So since it is pd, you can write it as sum p to the power half, p to the power half, and I might say p to the power half, p to the power half transpose. So you can write it as something into its transpose, some non-singular matrix into its transpose, and I have denoted by p to the power half. There are various ways by which you can get this, and one way is by the so-called Cholesky decomposition. And this may be obtained in R using a function called Cholesky. It is not Cholesky but Cholesky. So if you use the Cholesky function of R in Cholesky P, then you will get this p to the power half. Now once you get such a thing, you pre-multiply the entire thing by its inverse. So p to the power minus half, so to speak, that is inverse of p to the power half y, that is p to the power minus half x beta plus p to the power minus half epsilon. Remember, this is known, so you can consider this as your new design matrix, you can consider this as your new data, and this as your new error. If I call it epsilon, then epsilon has mean 0. It had mean 0, you have pre-multiplied it with something, still mean 0. It had covariance this, so now it is sigma square p minus half p half, and that is just the identity thing. So now you have reduced it to our familiar Gauss-Markov setup, and you can just proceed. So in this case, you do not really have to write down the likelihood function and try to maximize. This is simple. Now, one special case of this where P will be a diagonal matrix with strictly positive known diagonal entries. So if P is like this, diagonal say W1 to Wn, then p to the power half is very easily computed. It is just square root of W1 to Wn, diagonal matrix with square root of W1 to square root of Wn. And in this case, sometimes it is called weighted least squares, WLS, when P is of this special form. At least our textbook calls it WLS, weighted least squares. Now you can possibly guess that this setup is a pretty contrived one, because why should you not know sigma squared yet you know what is the multiplier of sigma squared? So you may be using two different instruments to make the measurement. So you believe that the two instruments are possibly of two different levels of precision. So it is okay to say one set is sigma 1 square and the other set is sigma 2 square, but how are you ever going to know what is the ratio between them? So you can never express one of them as sigma square and the other as exactly twice sigma square. You do not know the level of precision, but somehow you know it is exactly double the level of precision as the other one. That is a pretty contrived situation. So this GLS thing is more like of theoretical interest. However, it occurs as an intermediate step of a more general thing that we are now going to discuss.